Hello and welcome to exercise 3D.1, questions 13 and 14. Alright, question 13, diving straight into it. Consider the surge function ft equals at e to the minus bt when t is greater than or equal to 0 when a and b are positive constants. Prove that the function has a local maximum at t equals 1 on b. So really what that is asking us to do is to show that f dash t, the first derivative of t, is equal to 0, and the sine diagram of f dash t at 1 on b rather, and you can sub in 1 on b there, is a maximum, so positive and negative, it looks like that. Right, that's our goal. We need to find when f dash t is equal to 0, and hopefully it's 1 on b, because that would prove it. And then we need to show the sine diagram is positive, negative, to show it's a maximum. So, let's jump into that. First of all, differentiating. So here there are two functions of t. There's at and e to the minus bt. So we're going to use product rule, with u being at and v being e to the minus bt. Well, u dash is just a, and v dash you take is minus b e to the minus bt. You take the derivative of this top function, which is minus bt, bring it down, which makes it minus b, and then e to anything just stays the same. Alright, so therefore, f dash t is equal to u dash v, so a e to the minus bt, plus v dash u. So v dash is minus b e to the minus bt, and at. Alright, I'm going to do a little tidying here. I need some more space. ft is equal to ae to the minus bt. That makes a negative, and I'm going to put the at at the front. So it goes a, b, t. That's these three going to the front. By convention, you put them in alphabetical order, hence a, b, t, but really it doesn't matter. And then e to the minus b, t. Alright, that is it differentiated. We then wanted to set it equal to 0. So setting all of that equal to 0. It's a bit ugly doing it that way, but we'll get away with it. Alright, in any of these, we should be looking to take out a common factor. Now, the highest common factor is ae to the minus bt, which leaves us with 1. Take bt equals 0, because that is that and that. So we pull it out the front, and what we're left with is a 1 as a placeholder here, and then we've got the bt left over there. So, consider these two portions. Firstly, this one here. E to the power of anything will never be 0. A is a positive constant, so there's going to be no solutions coming from this side. This isn't very useful at all. But here is a little more useful. We can set that equal to 0. So we can write 1 minus bt is equal to 0. And we're looking for what value of t would make that equal to 0. So we're solving for t. And if I was solving for t, now I'm going to take 1 from both sides. So minus bt equals minus 1. And then I'm going to divide by minus b. The negatives will cancel, leaving me with 1 on b. Which is pretty neat, because it's exactly what I was after before. T equals 1 on b. Now, I need to prove that it is a maximum. So I'll draw a sine diagram. And frankly, if you're doing this in an exam, you can just put 1 on b here. This is t, not really a t, t and f dash t. And you know it's going to be positive, negative, because it's going to be a maximum. If you were going to show that by substituting values in, you choose a value less than 1 on b, So I would choose a value of 0, because you know that's less than 1 on b, because b is a positive constant. Positive constant. So you would choose 0, and you would sub it in here. If you subbed in t equals 0 to here, t equals 0, well, consider t equals 0. If t equals 0, well, that bit would go. So imagine eliminating it. So that just makes it 1 in the brackets. T is 0 here. Anything to the power of 0 is 1. A times 1 times 1, because A is positive, and then a positive times 1 and times 1 ends up with a positive there. To make something greater than 1 on B, I would write 1 on 2B. Is that going to be greater? No, it's going to be less. So 2 on B. We'll substitute that in, and it will work out to be a negative. All right, anyway, that's just the first portion. So that's done. All right, point of inflection. Point of inflection at t equals 2 on b. What this is asking us to do is basically show that f double dash 2 on b equals 0. So we're showing a second derivative is equal to 0 at 2 on b. All right, a good place to start from that is either here or here, because both of those are the first derivative. So to find the second derivative, we take the first derivative and differentiate again. I would probably go with this one. It won't actually matter in the end. All right, so if we take this here and aim to differentiate it again, what we will get is the first term here. Sorry, I'm not going crazy with colours. This first term, we do them separately. So first term, second term. The first term is quite nice. It will just differentiate to minus AB e to the minus bt. That comes from a being constant, so it just sits there. The power, you take the derivative of it. The derivative of that power is just minus b, and it drops down. And then the exponential stays the same. Then this next portion. This next portion is going to be plussed on here. But we have to do a little bit of work to get it. So in order to get that, we need to recognize that this is actually two functions again. There is the minus ABT, and then there is the e to the minus bt. So when they're multiplied by each other, we need to write them separately and do product rule. That's our u and our v. U dash is, well, that whole thing will differentiate to just minus ab. And v dash is minus be to the minus bt. All right. So then, using product rule, we're going to throw it up here. U dash v. So minus ab e to the minus bt. Then uv dash minus a b t v dash dot minus b e minus 3t. That email distracted me a little. This and that. All right. I'm going to buy myself a little space, and we're going to do some tidying here. So this first one stays the same, minus a b e to the minus bt plus. Now, a couple of things happen here. Well, actually, that plus minus just creates this to be a minus. A b e to the minus bt. Then this goes a little janky. We need to simplify those. That becomes a plus. And then we have that b's down the bottom. So b squared t e to the minus bt. Don't know why that became a 3, but that was meant to be a b. Alright, now same plan as before. We look to take out a common factor or simplify in any way we can. Interestingly, these two are exactly the same. Because they're the same, you can think of it as minus one lot of something and minus one lot of something. That's really minus two lots of a, b, e to the minus bt plus a, b squared t to the minus e to the minus bt. Alright, a lot happening here, but let's try and take out as many common factors as we can. Firstly, there's an a, there's a b, no, there's two b's on the side, but we still take one of the b's, and there's this entire thing. So we're going to factor out a, b, e to the minus bt. And what we're left with is minus 2, that's all that's left here, plus one of the b's, because we factored one out, and a t. And we want that to be equal to 0, because that's the second derivative equal to 0. Alright, once again, we look at each side. This side, you're not going to get a 0 out of it. A and b are positive constants. E to the minus anything, e to anything is never going to be 0. So our 0 is going to come from this portion here. Minus 2 plus bt equals 0. Once again, we solve for 2. Solve for t. I would add 2 to both sides. bt equals 2. Divide by b. t equals 2 on b. Which, very satisfyingly, is the point of inflection 2 on b. Pretty neat. Alright, sketch the functions showing the features you found. Alright. T, f of t. To start with, if t equals 0, looking at the original function, t equals 0, a equals 0. I mean, f of t equals 0. So we simply go through here. Now, what happens is we've got 1 on b and 2 on b. So 1 on b and then 2 on b is exactly twice as high as that. Now, we don't know exactly what that means in terms of numbers, but it will vary depending on what b is clearly. But we know that 1 on b will happen first, and then 2 on b happens twice the distance down. So what we're looking for is a turning point in line here. So we are looking for turns, an inflection point here. So now it's ugly, but that is where it goes from concave down to concave up, and this here is a maximum. All right. Now, without knowing the a's and the b's, you won't be able to sketch it more accurately, but that gives you the general form of a surge function, which is getting up really quickly and then down, and then plateaus down. All right. Go down and find 14. All right, consider the logistic function where a, b, and c are positive constants. Find the y-intercept. All right, y-intercept occurs when t equals 0, or the x equals 0. So here, if t equals 0, f of 0 is equal to c on 1 plus. That whole thing will be 1, so it's just 1 plus a. Whoop, lovely. Prove that c is a horizontal asymptote. All right, for this, asymptotes occur at extremes when they're horizontal. So vertical asymptotes shoot up at a certain point, but horizontal asymptotes flatten off into the distance, essentially. So what this graph is going to do is it will curve like this. It'll curve like this, and at some level, going into the distance, it will be c high. So to prove this, what we need to do is consider what happens when x goes towards infinity. Not x, t. When t goes towards infinity. It's on the x-axis. So what happens when t goes towards infinity? Well, we have c 1 plus ae to the minus bt. All right, so when t goes towards infinity, you're thinking, what happens when that gets really, really, really high? Well, when t goes towards infinity, minus bt goes towards minus infinity. The reason I know this is because it says b is a positive constant. So b is positive. Therefore, as t gets really big, minus bt is going to be multiplied out to get really small. All right. So this isn't so much a formal proof, it's more the logic behind it. And that's all you're going to need. Minus bt goes really, really small. Therefore, C on 1 plus a e to the minus bt. Actually, we'll probably skip a step. I'm going to go back, jump a step in. Therefore, e to the minus bt will go towards 0. So, what that's saying is if you take an exponential and have a really high negative power, like this, it gets very, very close to 0. So you can sort of convince yourself of this. If you do 2 to the minus 3, that would be 0.125. But 2 to the minus, 100 is going to be very close to 0. It'd be like 0.0000, and then like so many zeros, we're basically at 0. As soon as you get to that high negative power, you get very close to 100, very close to 0. So what's happening is, as t goes towards infinity, minus bt always goes towards minus infinity. E to the minus infinity gets very, very close towards 0. So, therefore, this actually gets very close to c over 1 plus a times 0, where that e to the minus bt gets very, very close to 0. A times 0 is nothing, so this is really getting close to c over 1, which is the level of that graph. Did I erase it off? That's inconvenient. So, c, or c over 1. What's happening is that as t gets really, really big, this entire portion here goes away to 0, leaving you just c on 1, which is the horizontal asymptote. Again, that's not a question that would be likely to be asked, but it's good to be able to understand where that's come from. Question 2 is something you'll be likely to be asked. If a is greater than 1, there is a point of inflection at the y-coordinate c on 2. Alright, that will take a little more work. So I'm just going to take that and bring it down here and we'll go again. Alright. Alright, point of inflection implies that we need to find f double dash t is equal to 0. And because then we're going to get the y-coordinate of c on 2, we need to find the t value and then sub it back in. Alright, this will involve doing either the product rule or the quotient rule twice. So, I guess we might as well start. If we're going to do this as product rule, our quotient rule, then our u is going to be c, our v is going to be 1 plus ae to the minus bt. u dash is 0, or 1. V dash is minus a b e to the minus bt. So the 1 differentiates to nothing, the minus b comes out the front, and you get that. Alright, so the first derivative, f dash t, is equal to u dash v, which is nothing, take v dash u. So that's minus abc, which is neat, e to the minus bt over v squared, 1 plus ae to the minus bt squared. Alright, first derivative, not too bad. Second derivative, so same again. U is minus abc e to the minus bt. V is 1 plus ae to the minus bt squared. U dash, well, differentiate this, is positive because the minus b is going to come down. A b squared c e to the minus bt. V dash, v dash, that 2 comes out the front. 2 bracket 1 plus ae to the minus bt multiplied by the derivative of the inner. Derivative of the inner, well, the a would 1 drops away. It's going to be minus abe e to the minus bt. Fun. So now we go on. We're doing quotient rule. So f double dash t is equal to u dash v, this pair, a b squared c e to the minus bt, bracket 1 plus ae to the minus bt, take u v dash. Now because there's a positive there, so there's a negative there, there's a negative here, and there would be a negative from the quotient rule. Overall, there is going to be a negative. Let's combine, well, just trying to figure out the best way to deal with the alphabet soup coming out. The a and the b will double up with an a and a b. That doubles up. So when you multiply e to the minus bt by itself, let's think about that, e to the minus bt multiplied by e to the minus bt. When you multiply something with a common base, you add the powers. So if you add these powers, you get e to the minus 2bt. So what we're going to have is minus a squared, b squared, c, because there's only one c, e to the minus 2bt, bracket, that 2 should go down here, 1 plus ae to the minus bt, close bracket. Oh, that's a mess and a half, over b squared. So then it just becomes 1 plus ae to the minus bt to the power of 4, because it was a power of 2. And we want all this to equal to 0. So really what we're looking for is this top line here to equal 0. Now, the top line is 2 terms, separated by that minus sign. And if we want them to equal to 0, an excellent place to start is factorizing. So, common factor. Let's just highlight the common factors in yellow. This entire thing is a common factor that can be pulled out. So let's just do that to start with. 1 plus ae to the minus bt, bracket, a b squared e to the minus bt minus 2a squared b squared e to the minus 2bt. All right. So that's common factor out. Let's take another chunk of factors out. We can take an a, we can take both b's. So we can take an a, both b's, we can take the c, we can take the e to the minus bt out. All right, so I'm going to move them right out the front. We can take one of the a's, we can take b squared, we can take the c, e to the minus bt. 1 plus ae to the minus bt. All right, let's see what's left here. We took that entire thing out, so that's left, minus 2. One of the a's was left. All right, so far so good. Let's consider which of these can give us solutions. And to consider that a little easier, we've shown that a is greater than 1. All right, so a is not negative, a is greater than 1. Now, I just paused because I realized I made a mistake. My mistake was when I pulled out this e to the minus bt, I took it out of there. The thing is, that's e to the minus 2bt. So there's one left over, meaning here, e to the minus bt. All right. Now, looking at this for solutions, a, b, and c are all positive constants. A is greater than 1. So, this term here will never get us a solution because e to the power of anything is always positive, and all the other a, b, and c are positive. Here, that will never get us a solution because it's 1 plus e to the power of anything is always going to be positive and non-zero. So, and a is positive, so that will always be positive. Our only solution comes from this one. 1 take 2a e to the minus bt equals 0. All right, so we want to solve for t. Solving for t from here is take 1. So minus 2a e to the minus bt equals minus 1. Divide by negative 2. A e to the minus bt equals a half. Divide by a, e to the minus bt equals 1 on 2a. Then, to get t by itself, we're going to have to take the natural log of both sides. So we do ln e to the minus bt equals ln 1 on 2a. E to the minus bt comes out the front here, so minus bt. Then ln e disappears, or doesn't disappear, it makes 1 multiplied by 1, we kind of ignore it, is ln 1 on 2a. Then we divide by minus 2. T equals ln 1 on 2a divided by minus b. Did I say minus 2? Minus b. Alright, that's pretty hideous. That is our answer though for t. When we then substitute that back in to the original equation, into here, where that t is, this whole thing will go to 1, because there'll be a 1 on a and an a, and that makes it c divided by 2, which is pretty neat. Sketch. I won't do, well, I will, I guess, sure. T, f of t. There's a horizontal asymptote at c, so c we're going to level off at eventually. And if a is greater than 1, then there is an inflection at c on 2. So c on 2 is half level of C. So what we have is going up very steeply here and then leveling off. And that is the inflection point. All right, that turned into quite a long video. Apologies. Good luck. Let me know if you need any more help.